Determining the formula of a compound. Now, I'm going to talk about this contraption up here just a little bit, not because it's something that's going to be tested on the AP exam, but this archetype of machine may be mentioned on the AP exam, and you may have to do something with data generated by this apparatus. And while this apparatus doesn't necessarily get you any points, just being familiar with what a question is talking about in general can help put your mind at ease and help you keep all of your faculties about you. So we will talk about this even though it's not going to directly result in AP exam points. When faced with a hydrocarbon, right? Hydrocarbon, so that's going to be hydrogen and carbon in some combination. When faced with a hydrocarbon compound of unknown formula, one of the most common techniques is to combust it, right, rapid oxidation, with oxygen to produce oxides of the nonmetals CO2 and H2O, which are then collected and weighed. So that means we are combusting something that is made of carbon and hydrogen. And so when you combust it, meaning react it with oxygen, the oxygen is going to react with the carbon to make CO2. The oxygen is going to react with the hydrogen to make H2O. And so by weighing the amount of CO2 that we have at the end, right, that is collected right here, I can tell how much carbon was in the original sample, because the only source of the carbon is going to be absorbed by the CO2 absorber right here. And yes, this sodium hydroxide is one of the most common ones. That is not going to be a question. What is a common carbon dioxide absorber? That's not going to be a thing. It's not going to be a question they ask you. They might tell you that it is an absorber, and so we're going to be able to tell how much CO2 we have, because that's going to be measured here. We're going to be able to tell how much H2O we have, because that's measured here. And that'll tell us how much hydrogen was present in the sample, because this is the only place for the hydrogen to go, right? All of the hydrogen that is here must have come from here. So when we move on to calculating empirical and molecular formulas, empirical formulas represent the simplest or smallest ratio, right? It's a ratio of elements within a compound, while the molecular formulas represent the actual numbers of elements within the compound, the actual numbers. It's kind of like the difference between prime numbers and regular numbers, whereas a prime number is some of the most simple types of numbers that you can see. They only have two factors, 1 and then itself, whereas the rest of the numbers, have multiple factors, right? They're a little bit more complex. That can be broken down in different ways. So the empirical mass is the least common multiple. So it is a multiple, right? We can divide or multiply into or out of it, and it is the smallest one of those. It's the most reduced as you can make it. It's the most reduced as you can make it. For example, CH2O is the empirical formula for a carbohydrate. And yes, all of the carbohydrates. Get it? Right? Carbo. What do you think carbo refers to? Carbon. What do you think hydrate refers to? If I tell you to go hydrate yourself, what are you going to go do? You're going to drink water. So carbo, carbon, hydrate, water. Broken down, this means carbon water. Carbon and water. Get it? Anyway, glucose is a perfect example of a carbohydrate, right? It's it's a simple sugar, and it should be very familiar to you coming out of biology, with an empirical molar mass of 30 grams per mole. An empirical molar mass. The actual molar mass of glucose is 180. So since the empirical mass is 30, that means that glucose is 6 units of this H2O, right? Because the CH2O has a mass of 30. You need 6 of those to get to a molar mass of 180. And we can write that as we have our carbohydrate, our generic carbohydrate, and we need 6 of them. AKA, what you're probably more familiar with is C6H12O6. All right? And so we're taking that empirical molar mass and we're multiplying it by 6 to get that molar mass of glucose, which is 180 grams per mole. So make your problem-solving life easy and assume a 100-gram sample if you're given information in percentages. So reading the AP exam, it gives you percentages if that's the case, if it starts with giving you percentages, which it might not, but if it gives you percentages, assume a 100-gram sample. What that allows you to do is it allows you to convert the percentages directly into grams. And then once you're in grams, you can convert into moles, and you're more than halfway there. Right? So just assume a 100-gram sample because we can just magically transform the percentages into grams. It makes our life a lot easier. A couple more terms that you might see that I don't want to confuse you. Hydrates. Hydrates. Just like carbohydrate, right? It was carbon water because of the hydrate. Waters of hydration. Waters of hydration. We actually dealt with one of these in Gen Chem on one of the problems that we worked. It turns out that if you remember that problem, we were supposed to figure out that the substance in question was copper sulfate pentahydrate, that there are 5 waters. This is a simple way to denote that there are molecules of water that cement the crystal structures together. And so in between the copper and the sulfate, the waters surround everything. And there are 5 of them that surround everything. Now, it's still the formula unit is copper and sulfate, right? Because those charges balance each other out, right? So that's copper 2, and that's sulfate. And so this is balance. It's not throwing anything off, but it helps cement the crystals together. And so this is copper sulfate pentahydrate. Another way to say this, it's commonly referred to as dot waters because we have the copper sulfate dot water. But we also have the anhydrous, right? An just means no, so there's no hydrous, so it means without water. It's kind of the opposite of a hydrate. Just calculate the molar mass of the anhydrous substances as you would any other substances, right? That shouldn't throw you off at all. This would be the only thing like, what? Oh yeah, there are waters attached to it. So let's get to an example. So a compound is composed of carbon, nitrogen, and hydrogen. So there for sure is carbon, there for sure is nitrogen, and there for sure is hydrogen. A 0.1156 gram sample, oh my gosh, this is how much of it we have. So we're going to combust all of this. We're going to react it with oxygen, right? AKA burned in air or combusted. We're going to react it with air. So I'm going to take this compound, there's 0.1156 grams of it. I'm going to react it with excess oxygen, because oxygen is pretty much always in excess. 0.1638 grams of carbon dioxide and 0.1676 grams of water are collected. So I have, let's see, that much of that. Oh, goodness. Sorry, I don't have that much of that. I have this much of the carbon dioxide. Okay. So, the compound, right, this much, plus O2 are going to react to create oxides of what was burned. So, whatever was present in this compound is going to create an oxide, right? And so, it's going to make carbon dioxide or dihydrogen monoxide, and then some nitrogen, right? So we know that carbon, hydrogen, and nitrogen are all present here. You can see that all of the carbon has to end up in CO2 because it's the only place that carbon could end up over here. So when in doubt, calculate the number of moles. So the problem, right? I didn't figure this out. The problem told me that there's 0.1638 grams of carbon dioxide. I'm going to divide this by the molar mass of carbon dioxide. You can add this up. It's 44.01, right? You can trust me. and you can convert that into a number of moles of carbon dioxide, therefore number of moles of carbon. Now, why are they the same number? Because for every one carbon dioxide, there's one carbon, right? So it's a 1-to-1 ratio. So I have the amount of moles of carbon. Next, you can see that all the hydrogen ended up in the water, the H2O. So calculate the number of moles. Right, the problem told me, again, I didn't figure this out, the problem told me that 0.1676 grams of water, I can convert that into moles of water using the molar mass of water, which again, adding up the mass of one oxygen, the mass of two hydrogens, I get 18.02 grams per mole. I come up with 0.009301 moles of water, which is H2O. But there are 2 moles of hydrogen for each mole of water. Again, for an example, think of an organ bank, right? You get one body into the organ bank, that means you get one heart, right? That's the same thing as having one carbon per molecule of carbon dioxide. Well, for every one body, you get 2 lungs, right? 2 lungs per body, in the same way, for every one molecule of water, you get 2 atoms of hydrogen, and so on and so on. So I have this many moles of H2O, therefore I'm going to need to double the number of moles of H2O to give the number of moles of hydrogen. So here's my number of moles of hydrogen. I double the number of moles of H2O, so I'll come up with 0.01860 moles of hydrogen. Therefore, the remaining mass must be nitrogen. Well, hold on. What do I mean remaining mass? What do I mean? Well, let's go back to the problem. I have a certain sample, 0.1156 grams of this compound. Right? 0.1156 grams of the compound. So, like I calculated on the last page, there are 0.003781 moles of carbon. Right there. There are 0.01860 moles of hydrogen, right? Just calculated right there. And I'll convert those into masses. I'll convert them into masses using the molar mass of each of them. And so when I do that for each of these, I come up with 0.04540 grams of carbon, and then 0.01879 grams of hydrogen. The reason that this is super important because when I add them together, I have the total mass due to carbon and hydrogen. Well, the total compound only has that much in it. So whatever's left must be the grams of nitrogen. So what do I do next? I subtract. So I have my 0.1156 gram sample. I subtract the 0.06419 total grams accounted for thus far by the carbon and the hydrogen. And that's going to give me my number of grams of nitrogen left, which is 0.05141 grams of nitrogen. Convert that into moles using the molar mass of nitrogen, and I have moles of nitrogen. So now I have moles of carbon, moles of hydrogen, and moles of nitrogen. I have moles of all three. So I must realize that the chemical formulas represent mole-to-mole ratios. All of these things represent mole-to-mole ratios. So I will pick the smallest number of moles and divide all the number of moles by that number. And that's going to be really nifty for me because it's going to guarantee me at least 1 0 in my ratios. Whatever isn't a 1, I might multiply by 1 or 2 or 3 to get the ratio to be small whole number ratios. So I notice that this is pretty much the smallest one. But notice how close these are, these two values. They're almost identical. They're off only by a little bit. So when I divide this by itself, I get 1. I divide this by the smaller number, it's essentially still 1. But when I divide this larger value by this, it comes out to be 5. So my empirical, remember the smallest whole number ratio, is CH5N. So this is my empirical formula. So if we are told that the molar mass of the original substance is 31.06 grams per mole, and I would reiterate, we are going to have to be told the molar mass. We can't just know the molar mass, right? That kind of defeats the purpose of the problem. We would have to be told the molar mass at this point. But we're told that the molar mass is 31.06 grams per mole. Then we simply use the relationship that the empirical mass multiplied by a multiplier will be the molar mass. So I add up the mass of the empirical formula, right? 1 carbon, 5 hydrogens, and 1 nitrogen. Again, 1 carbon, 5 hydrogens, 1 nitrogen. Notice that mass by itself is the same thing as the molar mass that was given to me already. You guys see how it's the same thing? That's pretty much the exact same thing as 1. If I'm going to solve for this, if I'm going to solve for n is pretty much going to be 1. So, in this situation, the empirical formula and the molecular formula are, in fact, one and the same. And it's not always going to be one and the same. If you go back to that quick example I used of glucose, right? The molar mass of glucose is 180 grams per mole, but the empirical mass is 30. So I'm going to have to divide that 30 into 180 to get 6. That's going to tell me that I'm going to have to multiply all of the subscripts in the empirical formula by 6 to get the correct value. So one more time as a summary, a little bit more concisely, hopefully, succinctly. Since mass percentage gives the number of grams of a particular element per 100 grams of that compound, base the calculation on 100 grams of the compound. Each percent will then represent the mass in grams of that element. Then determine the number of moles of each element present in 100 grams of the compound using the atomic masses of the elements present, right? Using your periodic table. Then divide each value of the by the number of moles. Divide each value of number of moles by the smallest of the values. If each resulting number is a whole number, after appropriate rounding, these numbers represent the subscripts of the elements in the empirical formula. If the numbers obtained, because they won't always be whole numbers, if they are not whole numbers, multiply each number by an integer so that the results are all whole numbers.